Today, we're actually going to look at chemistry a little differently. Instead of just memorizing a dry list of rules, I want you to think of it as this epic, cosmic drama about the invisible threads that literally hold our entire universe together. We're zooming way down into the atomic realm, a place where billions of tiny, glowing spheres are locked in a never-ending power struggle.
In a universe too small for the eye to see, their greatest desire is to hold onto the mysterious treasure known as electrons. Just think about that for a second. Electrons really are the ultimate currency of chemistry. You know, every single chemical bond you will ever study is, right at its core, a high-stakes negotiation over who gets to keep that treasure, and for exactly how long.
To make sense of these tiny negotiations, we've got to talk about one absolutely crucial concept, and that is electronegativity. You can basically think of this as the built-in power level for our atomic characters. It's measured using a dimensionless number on what's called the Pauling scale, and it simply tells us how strongly an atom can pull shared electrons toward itself. And it's pretty straightforward. The higher that number is, the stronger the pull. Okay, let's dive into Act 1, the perfect friendship. Our very first scenario is super simple. Imagine two identical atoms sharing electrons completely equally in perfect balance. Picture a sunlit valley where two identical hydrogen twins drift toward each other. Now, neither one is stronger and neither one is greedier, right? Their electronegativity power levels are exactly the same. So when they reach out to share their electron treasure, it's pure harmony. In that perfectly balanced friendship, which we call a nonpolar covalent bond, the electrons just hang out happily exactly halfway between them. But watch what happens when chlorine steps onto the scene, wearing its emerald armor of a massive nuclear charge. Let's say carbon offers to share an electron equally. Well, chlorine's pulling power is just way too strong. Those electrons are going to start drifting right over to chlorine's side.
Now, what's really fascinating here is that the electrons haven't totally abandoned carbon. They've just kind of packed up and set up camp over in chlorine's neighborhood. And that creates a polar covalent bond. Since electrons carry a negative charge, chlorine's side of the bond becomes slightly negative. We call this a delta negative charge. And carbon's side? Well, since it lost some of that nice negative cloud, it becomes slightly positive, or delta positive. It's not a full charge, it's just a really strong preference.
All right, things are about to escalate in Act 2, the ultimate theft. So, the plot thickens because we have sodium, and sodium practically wants to lose its electron to greedy chlorine. Poor sodium kinda shuffles in, holding its one single valent electron super loosely. It's way out there in the third shell, far from the nucleus, and really poorly shielded. I mean, sodium is basically giving this thing away. And, stepping out of the shadows to take it, our notoriously greedy chlorine atom. Remember, in a polar covalent bond, there's still at least some sharing happening. But when the gap in electronegativity gets huge, specifically when it crosses that 1.7 threshold, chlorine doesn't even bother asking. Snap, that electron is completely ripped away from sodium. Total transfer. Sodium turns into a fully positive ion, chlorine becomes a fully negative ion, and boom, they instantly lock together with this massive electrostatic force. And just like that, an ionic bond is born.
So this perfectly maps out the entire spectrum of our story so far. We go from the totally peaceful, perfect balance of hydrogen to that slightly tense, unequal sharing with carbon, all the way over to outright undeniable theft by chlorine. Literally everything in chemistry exists somewhere along this exact continuum.
Let's shift gears from the movie screen over to the laboratory for Act 3, the secret color map. Because if we want to actually see this invisible tug-of-war in real life, chemists use something called an electrostatic potential map, or EPM. You can think of an EPM as this incredibly cool holographic GPS system for molecules. It blooms with all these vibrant colors that show us exactly where the electrons actually live at any given moment. While going through the sources for this, I found the absolute best memory trick for reading these maps. It's simply red means rich and blue means broke. So, a red region on an EPM, that area is absolutely flooded with electrons. It's the delta negative side where the highly electronegative atom lives. On the flip side, the blue region is totally electron poor. That's your delta positive side, the poor guy who lost the tug-of-war.
So who actually wins these matches? Welcome to Act 4, the Grand Council of Atoms. Imagine all the atoms gathering together to rank their pulling power in this epic tournament bracket. Hydrogen steps up with a modest 2.2. Carbon flexes a little harder with a 2.55. Nitrogen pushes it to 3.04. Then oxygen strides in confidently with a 3.44. But then, the whole room just goes dead quiet.
A single figure rises from the back, fluorine. Sporting a maxed-out electronegativity score of 4.0, fluorine is the undisputed king. It's literally the ultimate schoolyard bully of the periodic table. Honestly, no one argues with fluorine. It has the tightest, most unbreakable grip on shared electrons of any element in existence, period.
Let's look at how this actual hierarchy of power shakes out. Down at the very bottom, you've got cesium with a measly 0.79. It's basically begging anyone to take its electrons. Sodium is right there with it. But as you move up the ranks through carbon and nitrogen, the greed really starts to ramp up. And by the time you reach oxygen at 3.44 and fluorine at 4.00, man, those atoms fiercely demand way, way more than their fair share. But why does this hierarchy even exist? Well, it all boils down to a super simple geographic rule on the periodic table. Electronegativity steadily increases as you move up and to the right. As you go left to right across a row, you're adding protons, which creates a much stronger pull from the nucleus. And as you go bottom to top, you have fewer electron shells. That means those outer valence electrons are physically closer to the nucleus. Less distance equals a massively stronger attraction. Let's gamify this a little bit and put it to the test. Carbon versus chlorine? Chlorine takes it, pulling the electrons away. Carbon versus oxygen? Oxygen wins that one easily. What about sodium versus chlorine? Total, absolute domination by chlorine, giving us that ionic bond. The golden rule here is so simple. The atom with the higher electronegativity always ends up as the negative end of the bond, for sure. And that brings us to our final chapter. Act 5, the dipole arrow speaks. To actually map all of this out on paper, chemists use a very specific symbol. Imagine a giant, glowing arrow pointing the way for us. It only ever points in one single direction, straight toward the inevitable destination of the electron cloud.
Think about the anatomy of this arrow. Notice the little cross at the tail end? That perfectly marks the positive end, the delta-positive atom that ended up losing the tug-of-war. The arrowhead itself is literally chasing the electrons, pointing directly at the greedy delta-negative atom. Follow the head of the arrow and you follow the electron wealth. It's that easy.
Okay, we've covered a ton of ground today, so here is your ultimate cheat sheet. Keep these 5 forever memory rules locked in. Number 1, the greediest atom gets the electrons. Number 2, the more electronegative atom becomes delta negative. 3, dipole arrows always point to the negative end. 4, electronegativity increases up and to the right on the table. And number 5, fluorine is the absolute highest.
At the end of the day, atoms aren't fighting over electrons because they hate each other. They fight because every single atom is just following its own fundamental nature. Chemistry really is just the never-ending story of attraction. So as you go through the rest of your day, look at the water in your glass or the plastic in your keyboard and ask yourself, who is secretly winning the invisible tug-of-war right in front of you?